Welcome to Praval. If you've tried building complex AI applications and found yourself wrestling with one massive, tangled prompt, this framework offers a different approach. Praval is a multi-agent framework for Python that lets you build sophisticated AI systems by combining simple, focused agents. You create an agent with a decorator, they communicate through messages, and you plug in LLM intelligence with a single function call. So here's what we're going to cover today. First, we'll look at why the traditional monolithic AI approach causes so many headaches. Then I'll introduce you to the coral reef philosophy, which is really the heart of how Praval thinks about multi-agent systems. We'll walk through the three core components: the reef, the spore, and the agent. We'll see how agents communicate with each other, explore the decorator pattern that makes everything so simple, look at some common design patterns, and finally discuss when multi-agent systems make sense and when they're overkill. All right, let's start with the problem. The traditional approach to building AI applications is what I call the God-agent pattern. You take a user query, feed it into one giant LLM prompt that tries to do everything, and hope for the best. Now, this works fine for simple use cases. But as your application grows, things start to fall apart. Here's what goes wrong. Your prompts become absolutely massive, sometimes thousands of tokens just for instructions. When something fails, good luck figuring out which part of that giant prompt caused the issue. Want to improve one capability? You might accidentally break three others. There's no specialization, so you end up with a system that's mediocre at everything instead of great at specific things. And scaling? Forget about it. You can't scale different capabilities independently. This brings us to the coral reef philosophy. The core idea is this: complexity should emerge from collaboration, not from individual complexity. Think about an actual coral reef. Each organism is simple and specialized. They communicate through chemical signals in the water. Together, they create a complex ecosystem. And importantly, if one organism dies, the whole reef doesn't collapse. So how does this translate to Praval? Well, instead of organisms, we have agents that are simple and specialized. Instead of chemical signals in water, we have spores, which are just messages traveling through the reef, which is our message bus. Complex AI systems emerge naturally from how these agents interact. And just like in nature, the system is resilient. If one agent fails or returns garbage, the others keep working. You can even build in fallbacks and error handling at the agent level. Let's get concrete. There are three core components you need to understand. The reef is your communication backbone. Think of it as the nervous system connecting everything. The spore is a message that carries knowledge between agents. And the agent is a specialized processor that does one thing well. These three pieces work together to create the whole system. Let's start with the reef. This is the communication backbone that connects all your agents. It's responsible for routing messages between agents, managing communication channels, handling asynchronous message delivery, and providing synchronization so you can wait for all agents to finish their work. In code, working with the reef is straightforward. You call get_reef to get the singleton instance. There's only one reef per application. To send a message, you call broadcast with your knowledge dictionary. And when you need to wait for everything to complete, wait_for_completion does exactly what it sounds like. Next up is the spore, which is just a fancy name for a message. Every spore has a knowledge dictionary containing the actual data you want to share. It knows who sent it via from_agent, who should receive it with to_agent, though that's usually none for broadcasts, and it has a spore_type that describes what kind of message it is. Now here's a really important convention. Inside the knowledge dictionary, we use a type field to determine which agents should process the message. So if you broadcast a message with type set to research_request, only agents that are listening for research_request will pick it up. This is how we get that loose coupling between agents. Finally, the agent. An agent is really just a specialized function that listens for specific message types, processes incoming spores, optionally calls an LLM when it needs intelligence and broadcasts results to other agents. That's it. Simple and focused. The key principle here is single responsibility. Look at this code. The agent decorator takes a name and a list of message types it responds to. Inside the function, you extract data from the Spore, call chat if you need the LLM, and broadcast your results. Each agent does one thing and does it well. Here's something that might feel different if you're used to traditional programming. Agents never call each other directly. There's no researcher.analyze or writer.compose. Instead, Agent A broadcasts a message with a certain type. The Reef delivers that message to all agents. Each agent checks if that type is in their responds_to list. If yes, they process it. If no, they ignore it. It's like a pub subsystem built for AI. This diagram shows it clearly. When we broadcast an analysis_request, every agent receives it. But only the analyst processes it because that's the only one with analysis_request in its responds_to list. The writer and validator see the message but simply ignore it. Let's look at the decorator syntax more closely. You write an agent with a name and your responds_to list. The function takes a Spore parameter, and inside, you write whatever logic you need. That's the entire API for creating an agent. But that simple decorator is doing a lot of heavy lifting behind the scenes. It creates the underlying agent instance with all its LLM capabilities. It subscribes to the appropriate Reef channels. It filters incoming messages so you only see the types you care about. It provides the chat and broadcast functions in scope. It handles all the async execution in thread pools. And if you enable memory, it manages that too. Inside an agent function, you have access to several key functions. Chat sends a message to the LLM and returns the response. Broadcast sends a Spore to all listening agents. You access incoming data through Spore.knowledge. And if you return a dictionary, it can optionally auto-broadcast. When you enable memory with the memory equals true parameter, you get additional capabilities. Remember lets you store something for later. Recall retrieves memories using semantic search, so you don't need exact matches. And get_conversation_context gives you the recent conversation history. Let's trace through an actual example. Here's a researcher agent that responds to research_request messages. It extracts the topic from the Spore, calls chat to do the actual research using the LLM, and broadcasts the findings with type research_complete. And here's a writer agent that picks up where the researcher left off. It responds to research_complete, grabs the findings, calls chat to write an article, and prints the result. Notice how start_agents kicks everything off by sending that initial research_request. Here's how that execution flows. We start by sending a research_request. The researcher receives it, calls the LLM, and broadcasts research_complete. The writer picks that up, calls the LLM again, and produces the final output. 2 agents, 2 LLM calls, 1 smooth pipeline. Now let's talk about common patterns you'll use. The first is the sequential pipeline. Input flows through agent A to B to C to output. Each agent broadcasts a message that triggers the next one. Perfect for multi-step processing where order matters. Pattern 2 is fan-out, fan-in. One input triggers multiple agents in parallel. They all do their work simultaneously, then results merge back together. This is great when you need different perspectives or analyses on the same input. The router pattern is like a traffic controller. Input comes in, a router agent examines it, and based on the content, sends it to the appropriate handler. Think of it as dynamic dispatch based on message content. Finally, the feedback loop. A generator creates something, a critic evaluates it. If it's good, we're done. If not, we loop back to the generator with feedback. This is fantastic for iterative refinement, like code review or content editing. So when should you use multi-agent systems? They shine with complex workflows that have distinct stages, like research, then analyze, then write. They're great when different expertise is needed, like having a domain expert, a writer, and an editor. Parallel processing becomes natural. Adding new capabilities is easy, just add a new agent. And in production, you can scale agents independently. But let's be honest about when it's overkill. Simple single-turn Q&A? Just use a direct LLM call. Tasks a single prompt handles well. Don't over-engineer it. And for quick prototypes where you're still figuring things out, the overhead might not be worth it yet. All right, let's wrap up with the key takeaways. Remember these 3 components. The Reef is your communication backbone. The Spore is your message-carrying knowledge, and the agent is your specialized processor. And these key principles, agents broadcast messages, they don't call each other directly. The message type field determines routing. The response_a list filters what an agent processes. And the @agent decorator handles all the wiring for you. That's the architecture. Now it's time to actually build something. In the next video, we'll open up the Hello World notebook and write our first Praval agent together. See you there.